Hello and welcome to Grokking Graph Analytics and Algorithms. I want to close this section by talking about Eulerian paths and revisiting the Bridges of Königsberg problem. This is a classic graph theory algorithm and not as pertinent to graph analytics, but it does have historical significance, so let's go ahead and dive in. Let's consider the following graph. We can find a path that visits each node exactly once by examination. This is what's known as an Eulerian path. If we had a path that started and ended at the same node and visited each node exactly once, that would be an Eulerian circuit. Let's consider the degree of each node. From this, we can think about finding Eulerian paths in a different way. Another way to think about this problem is that every node visited has to have an entry and an exit edge, except the start and end node. So we can see here, for example, that B can be entered here and then exited here. The same for D. We enter it and then exit it. You'll notice that A and C don't have matching entry and exit nodes. They have odd degree. This is okay because that odd edge out can be used as the entry or exit for the end of the algorithm. So, a way to quickly check for Eulerian paths is to count the number of degrees. If they're all even except exactly 2, you have an Eulerian path. So far I've only talked about undirected graphs. Go ahead and pause the video for a moment and think about how to check if a directed graph could have an Eulerian path. The requirements for a directed graph actually aren't any different, but the way the rule is stated has to be a bit more strict. To have an Eulerian path in a directed graph, you need to ensure each node has a way in and out. But now we have to check that the degree in and the degree out match. Then we also have to take care of the start and end node, which can have 1 extra degree in and 1 extra degree out. Let's consider the following graph. Its degree count is as follows. So we see that it meets the requirements for having an Eulerian circuit. We can identify a circuit here. And we can label the circuit as A, B, C, F, E, D. But we clearly haven't covered all of the edges. Well, the edges coming out of node C haven't been covered. So let's split the route open and cover this unexplored route. That is to say, we're only adding edges that we haven't visited yet. So we start at A and go to C, and that's this component, and then we cut the route open and we hit some unexplored edges. Let's cover CG and then GA. Well, we can also cover AE and EC. And now, since we've returned to C, we can tack on the rest of the route. And now we have a complete Eulerian circuit. This is Hierholzer's algorithm, which lets us find an Eulerian circuit. It works because we start with a working path and wedge in components that still work. Let's work through the pseudocode for Hierholzer's algorithm. This algorithm will take a graph as input, G, and return a Eulerian circuit. Let's start with an empty stack. and our Eulerian circuit EC as an empty list. We've already gone ahead and calculated whether or not an Eulerian path can exist, so we know the degree of each node. We're going to choose a current node. If all of the nodes have even degree, then we can pick any node. If exactly 2 nodes have odd degree, we pick one of those, and that'll be the start of our algorithm. We repeat this loop while we have unvisited neighbors for our current node, and our stack is not empty. If our current vertex has no unvisited neighbors, then we add it to the circuit. If the current node has no unvisited neighbors, then we add it to our circuit, and we also pop the next element in our stack. Otherwise, we add the current node to the stack, and then choose a unvisited neighbor from the list of neighbors for the current node. So that's Hierholzer's algorithm in a nutshell. In this section, we covered Eulerian paths. We talked about how to calculate if a graph has an Eulerian path, and we also defined Hierholzer's algorithm, which helps us find Eulerian paths. This algorithm has applications in very specialized graphs. That's undirected graphs where every node has even degree, or directed graphs where every node has equal degree in and out. You can perform a modified version of this algorithm that covers each edge at least once and minimizes the amount of repeats. This is known as the route inspection problem, and we'll cover it in a future section.